Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. So as you know, within this module we're trying to understand that how does the operating system manage the CPU by providing this abstraction of a process, right? And within the second module, we are now in the last topic, that is the sixth topic of CPU scheduling policy, right? So I started this topic in a previous video, and the basic idea behind a CPU scheduling policy, it's basically an algorithm, right? Which helps the CPU scheduler, which is a component inside the operating system, to select the next process that has to be run on the CPU, right? So we have been studying about this concept of CPU scheduling, and we know why we are doing this. Basically, we want to run more number of processes on a limited number of CPUs. That is why we need to time share the CPU among the different processes. Now, within this concept of CPU scheduling, a very important question that comes is that which process should run next, right? So this selection of the next process is done by a scheduling policy, right? And in the previous video we talked about this, that there is no one size fits all. No one particular policy can cater to different kinds of systems. There are a wide variety of systems, right? And depending on the computing environment, we have to select the policy. So starting from this video, we are going to look at the first type of computing environment, that is batch systems. We'll spend some time understanding about batch systems, what are the goals of these kinds of systems, what scheduling metrics have to be kept in mind, and finally based on these goals and metrics, which policies are suitable, right? And after that we will move on to the next type of systems, that is interactive systems, and then its policies. So in this video, let's start studying about the batch systems and the scheduling policies. So let us start the discussion by recalling what are batch systems, right? So as we discussed in the previous video also, so batch systems are a form of computing where the system takes a bunch of jobs, you can also call a batch of jobs, and then executes these batch of jobs, right? So the difference between a batch processing system versus normal personal computers versus interactive computing, the crucial part is that no users are sitting in front of the terminal. Like I'm currently shooting this video, I'm sitting in front of a computer system, it's a personal computer, right? Whereas in case of a batch system, there is no user which is sitting in front of the terminal and interacting with it per se directly, right? So in batch systems, obviously there would be some kind of user or operator which is submitting the jobs, or it could also be automated or scheduled. So there would be a bunch of jobs and it would be submitted to the system and they will be executed. But the user does not demand interactive performance, right? So this is the crucial part, that is the system is not designed to give like interactive performance or good response time. So this is the key characteristic of a batch system. So where are these kinds of systems used? So obviously they're not like in common use, right? Commonly we are all familiar, we are all using these personal computers, smartphones, laptops, right? This is the common form of computing. Obviously batch systems are less common and they have very specific purposes. And in early days of computing, they were actually common. There was no personal computing in those days. In early days, batch processing or batch systems used to be the default way of computing, but now it is used in more specific scenarios. Like for example, it is used in business and scientific domains. Let's talk about some examples. Let's say there is a company, and for every company there are several employees, and at the end of the month, the payroll or basically the salary of all of these employees have to be calculated, and this can be a complex process, right, and time consuming process. So what happens is that there would be a bunch of jobs that would be scheduled on a monthly basis, right, that would run on a monthly basis, and they would be calculating the salary of the employees. And if you see, this calculation does not require a person to sit in front of it and wait for like constantly monitor it, right? We can just launch the jobs and it will run in the background, and this is how batch systems work. Another example is that of interest calculation in banks. So in the banking system, people deposit their money, over which periodically certain interest gets accumulated, right? So again, if you see in this case, it's a periodic kind of job, it's a periodic kind of task, and it does not require much of user intervention. Once such a system has been in place, it can run in the background, right? So again, Also, the nature of these jobs are that they're bulk in nature. So when there would be interest calculation, it would be a heavy computation taking long time and would not require user to directly interact with it. So when I say user to directly interact, I mean in normal computing we are constantly giving some kind of input, for example web browsing, and we expect some kind of output. That kind of computing is not here, right? You just spawn these jobs, and they will run in the background, and when they are finished you can collect the output, right? And finally, in scientific domain, that is supercomputing, also where complex problems are solved, or at a let's say where statistic calculations happen. Let's say for a country, when governments make decisions, they have to like do that on statistical data. And when there's a whole bunch or whole bulk of statistical data, let's say at the scale of the whole population of the country, then for that kind of processing, again we need supercomputing, where batch processing would be followed, right? So these are some examples where batch processings are still used. They are still relevant, but the use case is much like specific, not very common. And the next point is that in batch systems, non-preemptive algorithms are acceptable, right? Because preemption is only required when we basically preemption is used for giving the opportunity to all of the processes, and that is relevant when we are trying to optimize for the response time, right? So in batch systems, response time per se to the user is not important. What is important is the throughput of the jobs, right? The turnaround time. So throughput basically is how many tasks or how many jobs are getting completed in a certain interval of time. We want it to be maximized. More number of jobs should be completed per time interval, right? And the turnaround time is also important. So turnaround time is basically the time it takes for a job, from the time the job has been submitted to the time it takes to complete. So the entire duration that the job or the task spends in the system is the turnaround time. We want it to be minimized so that task should get quickly completed. So that is the idea behind turnaround time. So you can see these are the possible goals. There could be more goals, but these are the important goals in a batch processing system. A user is not sitting in front of the terminal, so response time is not important. What is important is high throughput, that is more number of jobs getting completed, and minimum turnaround time or low turnaround time, basically jobs getting completed quickly. So basically more number of jobs in less number of time. That is the idea behind batch systems. And that is why non-preemptive algorithms are acceptable, because we can let jobs run for long amount of time, right? In interactive systems this is not the case. If we have a non-preemptive policy in an interactive system, then it could be the case that a particular job can hog over the CPU, it can run for hours, and when a particular job is running and we're not allowing other jobs to run, then that hampers with the response time. But that is not the case with the batch system. We can let the jobs run in whatever order, whichever maximizes the throughput or the turnaround time, right? In that way we can use non-preemptive scheduling algorithms in batch systems. So this was a overview of the batch systems. Now we will look at the metrics that are important in a batch processing system, and after that we will look at the different scheduling policies that are used in case of batch systems. So now we'll talk about turnaround time, which is the scheduling metric that we will use to basically judge different scheduling policies, right? So if we propose different scheduling policies or algorithms for batch systems, then how do we say that this policy is better than this one, right? How do we compare two algorithms? So in order to compare any two algorithms, we have to see how they are performing on a certain metric, right? This is why having a scheduling metric is important. And the metric that we are going to use for like policies, for judging the policies for batch systems, it is turnaround time. So as I said that throughput is also important, but going forward we'll look at turnaround time, which is more important than throughput, right? So what is turnaround time? So turnaround time, as we already discussed, is the total time a process takes from submission to completion, basically from starting till end. And it measures how long a process has spent in the system. This includes both the execution time as well as the waiting times. So the formula for turnaround time is that the time of departure, and you subtract from that the time of arrival, right? So if you consider any given process, there will be a certain time instant at which it will arrive in the system. We can say at, or the time instant at which the process has been created, right? Maybe the fork system call. And the time of departure is the time instant at which the process gets terminated. Let's say the exit system call, at which it calls the exit system call, right? So between these two time instant, what is the total time that has elapsed, right? That is known as the turnaround time. And The important part, if you notice, that in this turnaround time, both the execution time and the waiting time is included. What does this mean is that a process is not always executing on the CPU. Many a times, most of the times maybe, it is just waiting for the CPU, because the CPU is a shared resource and it might be in the control of some other process. So during that time, it is waiting. So turnaround time will include both the waiting as well as the execution time, or the burst time as we call it, right? So this is the definition of turnaround time, that is the total time that the process spends in the system. So let us understand turnaround time with some example. So let's take a hypothetical system which has a workload of 3 processes. So whenever we are judging basically any scheduling policy, we take a bunch of processes and see how they are executing using that policy. And that is how, by judging the metrics for these processes, we can see how good a policy is. So whenever we talk about a policy, whenever we take an example, we will talk about a bunch of processes and see how they fare using that policy, right? So let's take these 3 processes. So you can see in this table the arrival time and the burst time has been given. So burst time is the same as the execution time. Burst time is basically the time the process is executing on the CPU. It does not include waiting time. Only the time where the process is executing instructions on the CPU, that is the burst time. So here we are basically saying that process P1 will take 30 time units, right? Process P2 will take 50 time units, and process P3 will take 30 time units. A very important part, if you note here, is that we already know how much time a process would take in the system, but that is not generally the case in modern computing. When we are running a program, we do not know how long it will take, right? This is kind of an undeterministic problem, that you cannot determine beforehand how long a job will take. But for the sake of analyzing, for sake of study, we'll assume that we already know the burst time or the execution time of each process. This is a very important assumption that we are making, that we already know the time it will take before even running the process. So this we have to keep in mind. Only when we know the burst time, then we can uh, apply these policies, right? So now let us look at one example of how these processes could execute, right? So I have taken a hypothetical example. I'm not talking per se about any scheduling policy. I have just randomly ran the different processes in this following example. So our goal currently is to get familiar with how we will talk about scheduling policies, right? How we can judge the metrics and how we draw this diagram, right? So first of all, let's start with this diagram. So basically here we have these 3 processes, right, that we talked about in this table. And let's just say this is how they executed on a uniprocessor or a single processor system. So basically the operating system, it has time shared this CPU using some scheduling policy. It has time shared this CPU among these 3 processes. So we can see for some time P1 is executing, then P2, then P3, followed by P2, again P3 and P1. And this is how they have shared the CPU. So this is the diagram that you see, this is called a Gantt chart, right? So let me define what is a Gantt chart. So a Gantt chart is basically a generic kind of diagram, right? Just like you have pie chart, you have bar charts. Similarly, we have a Gantt chart, and it is also applicable to CPU scheduling. Not just CPU scheduling, anywhere we are talking about timelines, then a Gantt chart is a useful visualization. So basically, in the context of CPU scheduling, a Gantt chart is a timeline representation that visually depicts the execution order of process. This is important. It allows us to visually see how the processes are executing, what is the order first of all, and not just the order, their start time, their finish time, right, using horizontal bars, right? So let's come back to this diagram. So you can see, we can see for each process that during which time instant they were using the CPU, right? What is the order of execution? All of this we can see in the Gantt chart. So important thing is that on the x-axis, the horizontal timeline is basically an increasing time, right? And on that you draw the different horizontal bars for each process when they are executing, right? So we can see P1 was active during 0 to 20 and then 100 to 110. So P1 arrived at time 0, right? We know that it arrived at time 0. So, and it finishes at 110. So the total time it took is 110 seconds, which is what the turnaround time is. So using a Gantt chart, we can gauge the turnaround time also. Different metrics we can see. So let's talk more about this like diagram and how we can like see the turnaround time on this diagram. So we have discussed what is a Gantt chart. Like, let's come back to this, and now plot the turnaround time for each process. So for process P1, it arrived at time 0 and it finishes at 110. So the total turnaround time for this process is P1, sorry, is 110 milliseconds. We can see it was executing only for 30 milliseconds, right? Here 20, here 10, and for the rest of the 80 milliseconds, it was waiting, right? So turnaround time includes both the burst time as well as the waiting time. Similarly, process P2 arrived at time instant 10. For the initial 10 milliseconds, it was waiting. Then it got to execute for 30 milliseconds. Then again for 10 milliseconds, it had to wait. And then it got 20 milliseconds. So 50 milliseconds, it was executing, 20, it was waiting. So the turnaround time is 70. Similarly, for process P3, it came at 20 and finished at 100. So the turnaround time is 80, out of which it spent 30 units on execution and 50 on waiting, right? So we can basically calculate the turnaround time in this way, that is completion time minus arrival time, which has been listed here. So this basically gives you an idea of what is turnaround time and how we can calculate it. Also, how can we visualize it is on the Gantt chart. So this was about the first important metric. Then a related metric, or we can say a metric which is directly derived from turnaround time, is the waiting time, right? We want turnaround time and both waiting time to be minimal. So let's see the formula. Turnaround time, as we already discussed, is calculated as the time of departure minus the time of arrival. That is the total time the process spends in the system. We also said that the turnaround time is composed of burst time and the waiting time. Now the burst time is fixed, right? For any given process, before even running it, we know the assumption here is that we know the burst time of each process, and that is fixed. So since burst time is fixed, then turnaround time is kind of proportional to the waiting time. So the longer the waiting time is there, basically burst time is also a component of turnaround time, but what will finally determine the turnaround time is how much waiting time is there. So the higher the waiting time, the higher the turnaround time, right? And similarly, the lower the waiting time, the lower the turnaround time. So waiting time is also important. So we can calculate the waiting time using this formula, that is turnaround time minus burst time. This is something which we are also interested in apart from turnaround time. So again, coming back to this example, we can just apply this formula, that is waiting time we can get by subtracting the burst time from the turnaround time. So 110 minus 30, 80, 70 minus 50, 20, right? Similarly, 80 minus 30, 50. And let's also visualize these waiting times. We already discussed this, but let me also show it once again on the Gantt chart. So you can see for process P1, the entire turnaround time is 110, out of which 30 it is spending on execution. We can see 30 is the burst time, and this remaining 80 milliseconds in between is the waiting time. We can see the waiting time is for process P1 is 80. Let's come back to process P2. The arrival time is 10, the finishing time or at the end time is 80. So 80 minus 10, 70 is the turnaround time, and now from 70 you subtract the burst time. 70 minus 50 is the 20, so 20 is the waiting time. Similarly, for process P3, arrival time is 20, the finishing time is 100, so turnaround time is 80, and from that you remove the 30 milliseconds of execution or the burst time. So 80 minus 30 is 50, 50 you get the waiting time. So these are the two important metrics that we will be concerned about as long as we are talking about batch systems, right? So very important point is that we are currently concerned about batch systems, and the goal that we are optimizing for in batch systems is turnaround time, right? So both turnaround time and waiting time are important, and going forward, when we talk about the different policies, we will compare each policy on how they are faring on these goals or these metrics. Any policy that minimizes the turnaround time or minimizes the waiting time is a good policy, and vice versa. If there is a policy which is performing badly, that is having a high turnaround time for the process, then that is not something which we will prefer for batch systems. So this was about the scheduling metrics that we will follow when we are talking about batch systems. Now, having discussed the policies, the metrics, now let's focus on the policies which we will study in this topic for batch systems, right? So there are three algorithms or three policies which we will talk about through this entire topic. They are first come first serve or FCFS. Each of them is known by their acronym, right? One is shortest job first and the other is shortest remaining time first. So these are the three different policies or three different algorithms about which we'll talk in detail from the next videos. I'll not talk about them in this video, right? From the next videos, we'll talk about them in detail. But just to give you a context, like how these policies were derived, basically all of these policies have been derived. These are early policies. Why are we saying that these policies are early policies? Because they were used during the early days of computing. Batch processing was relevant in the early days of computing. Now modern computing is more based on personal computing, right? So these policies are no longer relevant today, but basically no longer relevant, I say, because not used in personal computers. They are used in batch computers, which have which were more popular and common during the early days of computing. So these policies are kind of old, right? And they have been derived from fields like operations, manufacturing, assembly lines. Basically, whenever you talk about industries, right, where production is happening, there are tasks, right? And there is also a desire for efficiency, right? Just like we have multiple tasks or multiple processes in the computer system to which we are trying to allocate this resource. In the same way, this same need for efficiency is exists across all of these manufacturing lines, right? So these policies have been derived from the world of manufacturing, where these policies are relevant, right? So we'll talk about these policies in throughout the next videos, right? So within this video, basically we had like a brief introduction or a brief recall of what are batch systems. Then we talked about what are the different metrics that are important for batch systems. We talked about turnaround time, right? We talked about waiting time. We also learned about what is Gantt chart. And finally, we talked about what are the policies that we are going to study as part of batch systems. There are more policies and more computing environments. So when we talk about the interactive systems, then the policies that we'll see will be different. But for batch systems, these are the three policies. And finally, as I said, these policies have been derived or have been influenced from or basically similar algorithms are used in manufacturing lines for efficiency, right? Throughput and turnaround time, these are like goals which are relevant in manufacturing also, right? So we want as many tasks to get completed in and the task to take lesser amount of time. So throughput is required, high throughput is favorable, and low turnaround time is also required in manufacturing line. So that is why these policies, these algorithms have been kind of derived from these areas, right? So guys, this was it for this video. Thank you very much for watching. I'll see you in the next video. Thank you.